All right, welcome. Today we're going to cover section 5.1 and 5.2. I will keep some things brief, but I will tell you this, if you don't recall a lot of the material that I mentioned that you might recall from Algebra 2, it would probably be a good idea to brush up on those skills. 5.1 is going to essentially remind you about the unit circle, so you should have learned about it in Algebra 2. And I'm going to go at it from that lens rather than going into great detail on the construction of the unit circle. Okay, so you're going to understand how to design it, how to visualize the angles and reference numbers on it. And I would say if you can't recall this, this is what I would spend some time on. So the unit circle, very quick reminder, it all stems from your special right triangles. So I have two pictures here of your 30, 60, 90 and your 45, 45, 90, which you studied in geometry, and then again when you constructed the unit circle. So if you don't recall this at all, I would maybe jot down these pieces so you can refer to it if needed later. But notice your 30, 60, 90, for example. Opposite of your smallest angle is your smallest side. Opposite of your middle angle is your middle length side. And opposite of your 90 biggest angle is your biggest side. So just kind of reminding you where those stem from. Same goes with the 45, 45. Those ratios are 1, 1, and square root of 2. So on the unit circle, first of all, the unit circle, just reminding you, has a radius of 1. So anywhere I go on the circle, clearly I'm going to have a radius of 1. So if you look at this picture right here, I kind of slid in the 30, 60, 90 triangle. Well, the radius is supposed to be 1, and clearly on your geometric triangles put into unit circle, it's not 1, right? It's 2. So the issue is taking this triangle from what you know, taking the ratios, and now we have to make this length of 2 over here, we have to change it to 1 to put it into the unit circle. So easy fix, divide it by 2, right? If I divide this by 2, that's going to be 1. Well, then I have to divide all of the other ratios by 2 to balance that out as well. So in construction, it would look like that. Okay, so now on the unit circle, if I said, what is the sine of 30 degrees? If you recall SOHCAHTOA, actually while I'm here, if you don't recall SOHCAHTOA, you should probably write that down as well. So sine, cosine, tangent, and then the opposite and adjacent and hypotenuse pieces that go with it. So if I asked you what is the sine of 30 degrees, for example, according to my unit circle, I can, so this triangle right here now is a 30-degree angle, and I know that sine ratio is opposite over hypotenuse, so opposite is 1/2 and hypotenuse is 1, and 1/2 over 1 is clearly 1/2. Okay, now the good news is if you didn't derive this from the unit circle, I could go back over here and use my regular geometry triangle as well. So if I said sine of 30 is opposite, which is 1, over hypotenuse, which is 2, and I still get 1/2. Okay, but I would highly encourage you to go away from your geometric triangles, like as soon as you possibly can. So going with the blue triangle here in terms of the unit circle. Okay, same thing, and I'm going to go through this one a little more quickly, but if I pull my 45, 45, 90 onto the unit circle, so you can see my 45 degree, and I have my ratios there, but again on the unit circle, the radius needs to be 1. So to fix this problem, because my radius is currently the square root of 2, I need to divide by the square root of 2, which means to balance, I have to divide all of my sides by the square root of 2. Okay, and you probably also need to recall that in order to rationalize those denominators, because you don't want to divide by a square root, a radical, I need to multiply the top and the bottom by the square root of 2 over the square root of 2, which is then going to give me this green triangle here. Okay, and these are my unit circle pieces. So take note of my radius is now 1, that's great. My other 2 sides, which are going to be sine and cosine values, are square root of 2 over 2. Okay, and I'm just going through these kind of quickly. Last but not least, 30, 60, 90. Again, on a unit circle, I need the radius to be 1. So right now it's 2. To fix that, I divide everything by 2. Easy fix, easy fix, easy fix. And in that summary, you can see in the blue triangle would be my unit circle ratios for the 30, 60, 90. Okay, again, taking note, the radius is now 1, which is what I want. And my lengths are square root of 3 over 2 and 1/2, which are going to be my cosine and sine values. Okay, so now I'm going to put this all together. Here is your completed unit circle, which again, you spent some quality time on in Algebra 2. It is going to seem overwhelming right now because you might not remember a whole lot about it. Study this, spend some time on it, derive the pieces. Things aren't going to get easier for you if you put this off. So that should be priority. But if you look at the unit circle, if you look at your 30, 60, and 90, 30, 45, and 60 degrees, which I just talked about their triangle pieces, notice the coordinates over here, square root of 3 over 2, comma 1/2. The coordinates at the 45, square root of 2 over 2, square root of 2 over 2. These should be familiar, right? They all come from that special right triangle. 60 degree coordinates as well are just opposite of your 30 degree, right? That should probably make sense because the 30 and 60 degree triangles share sides. So that being said, those key pieces that I have underlined in red, those are your cosine and sine values for that particular degree angle. So 30 degrees, for example, has a cosine value of square root of 3 over 2, and it has a sine value of 1/2. Okay, so rather than constructing the triangles, you can just refamiliarize, possibly memorize those again. What it's measuring, of course, is the lengths, the ratio lengths of your unit circle. So if I know that the radius is 1, then to get to this point right here, I know the cosine will be the length of the square root of 3 over 2, and the sine will be the length of 1/2. So that's really what you're finding is those distances. So it probably makes sense when I go to the 60 degree angle from my origin, to get to this point, I'm going over, which is cosine, a much shorter distance, and going up sine a longer distance, right? So the blue horizontal length is the same as the green vertical length. You can probably visually see that, even though mine is, not perfect. So just to summarize, since I keep referring to this, your cosine of any angle is going to be the x-coordinate, sine of the angle is going to be the y-coordinate, and then tangent, which we'll get into more detail later, but you'll want to make note of that as well. The tangent ratio is y divided by x, or sine divided by cosine, if you prefer. Okay, other things to notice on the unit circle is the reflective properties. So if I go over here to 120 degrees, notice that 120 degrees, the coordinates are the same as the coordinates of the 60 degree angle, except for the x or cosine is negated, which makes sense because you're going into the second quadrant. Okay, note when you get into the third quadrant, all of the sine and cosine values are negative, which makes sense. X, y, cosine, sine, everything is negative in quadrant 3. Quadrant 4, notice only the y coordinates or sine values are negated. Okay, so things that you're going to need to kind of refresh your memory on. The other thing that you're going to need to, remind yourself of is how to get the angles in radians. Okay, so I'm going to erase all of my stuff here so you can look back at the unit circle. And maybe take a screenshot of this unit circle or just Google unit circle and you'll have ample pictures to look at. But on this unit circle, the 30 degree in radians, and I know it's kind of little, you need to zoom in, but the 30 degree angle in radians is pi over 6. Okay, you will need to know both of those, degrees and radians. That being said, if I reflect over the y-axis, the 150 degree angle has a radians of 5 pi over 6. Notice both radians are in terms of sixths, right? 1, 6, 5, 6. Go down in the third quadrant where 210 is going to have the same coordinates, right? All of these coordinates here are the same, just the plus and minuses change. And notice its angle in radians is 7 pi over 6. Okay, and lastly, in the fourth quadrant, at 330 degrees, notice its radians is 11 pi over 6. So all of the angles that reference the 30 degrees in all four quadrants have radians that are sixth. So 1, 6, 5, 6, 7, 6, 11, 6. And again, you'll want to be familiar with that. Okay, the rest of them I'll go through just quickly, but you can also note that the thirds, so 60-degree angle in radians is pi over 3. Okay, well then 120 degrees is 2 pi over 3. They're all thirds. So then I will scroll down so you can see that. 240 degrees is 4 pi over 3. So another third. And last but not least, in the fourth quadrant, 300 degrees is 5 pi over 3. So those are all thirds. And then the fourths are the same. So the 45 degree is pi over 4, 135 is 3 pi over 4, 225 is 5 pi over 4, and 315 degrees is 7 pi over 4. Okay, all it is fractions. So if you want to think about it, because you're also going to have to know the quadrantal angles, like the 0 degrees, the 90 degrees, the 180 degrees, the 270, you can just break this unit circle into sixths and fourths, and you'll get everything. Okay, so I'm going to erase all my colors here again, and just kind of show you that quickly, and then we're going to need to move on beyond this. Okay, so if I start here at my unit circle, this is 1/6 of pi. Okay, and I probably should reference pi is over here. So pi is the radian measure, equivalency to 180 degrees. So if I start here, this is 1/6. Okay, then if I break it into 2/6, well, what is 2/6? 2/6 reduce is 1/3, right? So I got pi over 6, pi over 3, so there's 1/6, 2/6, 3/6 would be right here. 3/6 is pi over 2 reduced. 4/6 would be this sliver, and 4/6 reduced is 2 pi over 3. 5/6 right here, and 5/6 doesn't reduce, and then of course 6/6 I'm to pi, right? And 6/6 is pi. And then you can keep going, and I'm not going to keep writing these all out, but this would be 7/6, and the next one would be 8/6, which reduces to 4/3, and 9/6, which reduces to 3/2, and 10/6, which reduces to 5/3, and 11/6. Okay, now you have every radian measure on the unit circle except the fourths, but those are pretty easy. So if I highlight those in blue, this is 1/4, 2/4 overlaps, 3/4, and 4/4 overlaps, 5/4, 6/4 overlap, and 7/4 and 8/4, you're to 2 pi. So if you recall, the unit circle full rotation is 2 pi radians. Okay, now there are other videos out there if you need more background on the unit circle, but we're gonna move on and do a whole bunch of stuff with it. So the first thing you have to recall is probably what you call the reference angle in Algebra 2. In your pre-calc book, it's called a reference number. It's the same thing. Okay, so reference number, first and foremost, notation, is T with a bar above it. Okay, so a reference number is the shortest distance between the terminal point of the angle and the x-axis. Okay, you need to know that, and then I'm going to clearly give you some examples. So the shortest distance from the terminal point of the angle and the x-axis. Okay, so for example, if you have 4/3 pi, okay, so T is 4/3 pi. This right here is your angle. Okay, so first thing you probably want to do is visualize it, and how I do this is I look at the if it's a degree in radians, I look at the denominator. Since it's a third, I know that pi is going to also be a third, so I would just make that 3/3. Okay, well, if you visualize when you draw an angle, you always start at the x-axis and then you go counterclockwise. So if I go all the way to 3/3 and then another 1/3, that would bring me to 4/3 pi. Okay, so this angle, if I draw it in right here, that angle is 4/3 pi. Okay, That's not what the question is asking, however. It's asking for the reference number. Okay, so now the reference number is the shortest distance from the terminal side to the x-axis. Okay, so the red is my terminal side. The x-axis, I could go this way or I could go this way. By definition, it's the shortest side. Okay, so I don't want this one here, so I will erase it. So the shortest side from the terminal side of the angle to the x-axis. What does that measure? Well, if you think about what I said verbally as I was drawing the angle, I go all the way around, I hit 3/3, and then another 1/3 is gonna bring me to 4/3. That another 1/3 right there, that's my blue reference angle. So T with a bar above it, reference angle, is 1/3 pi, or pi over 3, however you want to write that, probably pi over 3. Okay, so again, if you think about the black angle is 3/3 pi, plus another 1/3, your reference, brings you to your angle of 4/3. Okay, let's look at another one. So what if your angle is negative 7/6 pi? Okay, so negative is gonna go clockwise now, so go the opposite direction. And my angle is a 1/6, so my pi is now gonna be 6/6, but it's also negative because I'm going clockwise, right? So if I start at my x-axis, and then I'm gonna go around 6/6 pi, negative 6/6 pi, I should say, so that's negative pi. To get to 7/6, I would have to go one more 6 beyond. So again, if I draw this entire angle, this angle here is negative 7/6 pi. Okay, so what do I reference? The shortest distance from the terminal side of my angle to the x-axis. Clearly not gonna be this because that's not the shorter distance. So from the end of your angle, this red line, to the x-axis. So what does that measure? Well, if this whole thing is 7/6, and this angle over here is 6/6, the leftover extra is 1 more 1/6. So T bar, reference number, is pi over 6. Now, something else you want to know, reference angles are never, never negative. So even though you're going in the negative direction clockwise, reference angles are always positive. All right, maybe pause the video and try these. See how you're feeling about this. Okay, I'm gonna talk through these a little more quickly, assuming that you've paused the video and spent a little time on that. So your angle is 14/5. So again, my pi now is gonna be fifths. So I'm gonna make that 5/5. All the way around 2 pi would be 10/5. Okay, so I'm gonna go to 14/5. So if I go all the way around, that's 10/5. Plus another 2.5 would bring me to 12.5/5. All the way to 14/5. Okay, so let me just change this. This would be 15/5. So if I keep adding 5/5, like every increment of pi is another 5/5. So I'll show you with my red pen again. This all the way around is 10/5. Plus another 4 would be 14/5 pi. That red angle kind of shows the path of that. So what is it referencing? Well, again, from my terminal side to the x-axis, that's this sliver. So if my red angle is 14/5, how many more to get to the x-axis to get to 15/5? Well, 15/5 minus 14/5 is 1/5. So that reference angle is pi over 5. Okay, the last one, T is 2.5. And that one's unique because there's no pi in it. But it's not degrees because there's also no degree symbol, so please don't confuse that. But 2.5, well, I know if this is pi, I'm just going to write 3.14 because we know that that's pi. So 2.5, if I were to approximate that, is a little before 3.14. Okay, so there's my angle. Well, my reference angle is from my terminal side to the x-axis. So mathematically, how can I figure out what T bar, my reference number, is? I can take 3.14 minus 2.5 and get that as an approximation, or if I want it exact, I can take pi, 3.14 is pi, minus 2.5. And probably in WebAssign, they're looking for this exact answer. Obviously, if you approximated it on a test or something, that would be fine with me, but for WebAssign, I would stick with exact values there, but just to kind of understand numerically what you just found. Okay, one thing I guess I didn't cover is what if you have an angle that's in degrees. So for example, if your angle is 70 degrees, okay, well this is 180, this is 90. So if you were going to approximate, no, I don't want to make this 70, that's no fun. Let's just make it 110 degrees. Okay, so if I visualize the angle, well if this is 90 plus another 20 would bring me to 110 degrees, okay? And if you think about as you're drawing the angle, I just said the reference angle. I said this is 90 plus another 20. I'm sorry, that's not the reference angle, but that would give me the 110. So now the remaining to get to 180 is my reference angle. Okay, so again, if this is 110, how much more to get to 180? Well, of course, you can obviously do the math as well. So 180 minus 110, and that reference angle, reference number, reference angle, same thing, is going to be 70 degrees. So there, it's the same way in degrees. All right, on to a little bit more with the unit circle. I did not reference the equation probably to the unit circle, but you should be familiar with the equation of a circle in general. So x squared plus y squared equals 1, specifically for the unit circle, because if you recall, that 1 will give you a radius of 1. So if you're asked to show that a point is on the unit circle, you just need to prove mathematically that x squared plus y squared equals 1. So if this is the point, x and y, then you are, like I said, you're just proving that math right there. So square root of 11 over 6 squared, x squared plus y squared equals 1. And then I'm guessing you can handle the math, but squaring everything inside the parentheses, so that will be 11 over 36 plus 25 over 36. And does that equal 1? Yes, because this is 36 over 36. Which obviously is 1. So I just showed, yes, that is on the unit circle. Okay, so pretty basic. You might have to work a few things backwards, so you might have to find a missing coordinate given some information about the unit circle. So we are going to figure out what the x coordinate is. Please note that you're in the 4th quadrant, and in the 4th quadrant, x is positive and y is negative. So okay, I'll come back to that. You're probably like, yep, duh, got it. If I use x squared plus y squared equals 1, y squared, so I will just plug this in, equals 1, right? So plugging in the coordinates and squaring everything, you get 49 over 625. Okay, and then it's a little bit of algebra. So I'm going to subtract over the 49 over 625, and common denominator says that 1 would be 625 over 625, and when you subtract those, let's see, 625 minus 49, that'd be 576, and then to solve for x you would square root. Again, I'm just kind of going through the algebra quickly, assuming you're okay with this. Technically, this is going to be plus or minus, let's see, the square root of 576 is 24, square root of 625 is 25. Now I have to make my decision on the plus or minus based on the quadrant that I'm in. Just always pay attention to quadrants, such a big deal in this chapter. So because I'm in the 4th quadrant, right, then I know that my x coordinate is positive and not negative there. So there I have the other missing x coordinate. So 25 or 24, 25th.